Yeah, what's the deal? Let's see what happens. So what'd you do? What's algebraically, what do we do here first? Distribute the -1. Okay, good. Distribute the -1. So then that gives us, oops, frozen. Okay, so when we distribute the negative, that's going to give us what over here? -3, okay. And then on this side, if we combine those like terms, good, -2c, everybody agree, 5c plus -7c, okay, plus 3. We could combine the 6 and the -3 then, right? So we're going to get 3 minus 2c, and over here we have the same thing. If I flip that around, it doesn't really make any difference to order, does it? And so, now what? If I add 2c to both sides, what happens? Yeah, if I combine the like terms of the variables, I just get the statement 3 equals 3. Okay, any suggestions what that means? That's weird. Perfect problem? I mean, there's something unique about it, for sure. Any ideas? Normally, what would we do if we got an answer like c equals 5? How would we check? We'd plug it back in. This time it didn't really give us anything to check, did it? Okay, what if, let's just try a value. What if I put in 0 for c? That's an easy one to check. If I put in 0 for c, what would happen? Let's just see what we get. If I plugged in 0, that term would go away, wouldn't it? Yeah. Everybody agree? So I'd have 6 minus 3 is, I get 3 on this side, and over here, that term would go away, and that term would go away, and I would just get 3 equals 3. So 0 worked. Is 0 the solution? Did I accidentally get it? Seems like it's a solution, isn't it? Let's try 1. What happens if I put in 1 for c?
It wouldn't work.
If I put in 1, I'm going to get, that's going to become a 2, isn't it?
Yeah.
So I'm going to get 2 plus 3 is 5, everybody agree? And 6 minus 5 is 1. How about over here? I'd get 5, right? If c is a 1, I get 5 plus 3 is 8, minus 7 is 1. That worked also. If I plug in 1. What do you think is going to happen if I plug in 139? It's going to work. What if I plug in -77? It's going to work. In fact, I could plug in any number, couldn't I? So how do we interpret this? If the variables go away completely, if they disappear, but I end up getting a true statement, something that is true, then the way we think about that is it always works. 3 is always equal to 3, and so the answer is to this is that c could be any real number. All real numbers would work. Okay? Does that make sense? That's a strange case, but we'll see stuff like that. Okay, what would have happened, do you suppose? Let's just say hypothetically that instead of getting a true statement like this, what if the c's disappeared, but what if we ended up getting something like 4 on the left and 6 on the right? What do you think is going to happen there? No matter what value of c I plug in there, the c's are going to go away, aren't they? Right? And I'm going to be left with an untrue statement. So is any value of c going to work? No. So how do you think we'd say that answer then? What's the solution? There's no solution. Yeah. So if we got something like this, oops, that would be the case where we have no solution. When the variables disappear, but we're left with an untrue statement. Okay? Make sense? Okay, and we'll explore that in more detail later. We'll compare. We'll look at some graphs, for example. When we deal with quadratics, we'll come back and revisit this, and you'll get a little more insight into why it's that way. I want to move on. What about something like that? That is, in one way, it's harder, and in one way, it's easier than the problems you've been doing that we ended up with yesterday, the one you just did today. It's easier in the sense that there is no distribution to do. There aren't that many terms. But what's the obvious reason that's maybe a little bit harder? Fractions, yeah. Fractions, now let's just make this clear right from the start. Fractions are just numbers, but they're kind of tough numbers to work with, right? It's more tedious. You add and subtract and multiply and divide fractions just like you do with integers, right? But they're harder to work with. There's a bigger chance of making a mistake. And so with a problem like this, if we were going to just dive into this and try to do the same stuff we did before, really all we would do is just combine like terms, right? There's not a whole lot to do here. I would want to combine the x terms. What's bigger, 3/5 or 1/6? And would everybody agree that x over 6, that x over 6, that's the same thing if I wanted to write it as a fraction times x. I could write it as 1/6 x, right? Everybody see that? Because if I multiply 1/6 times x, x is really the same thing as x over 1, isn't it? And we just multiply fractions straight across. So either way you want to write it, it doesn't matter. They mean the same thing. So if that's 1/6 x and that's 3/5, isn't 3/5 bigger than 1/6? So I would have to subtract 1/6 x from both sides. But once again, I got to deal with fractions there, right? And I could do it that way, but there's a shortcut. Does anybody know the trick, a way to just get rid of the fractions in this situation? We can't cross cancel on this one. Okay, and that's an idea that people, other classes have suggested that too, and it's not a bad idea, except let's talk about why in some cases that works and in some cases it doesn't. 3/5, what is that as a decimal? 0.6, exactly, isn't it? 0.6 is exactly equal to 3/5. That's a good trade, right? That works. 3/2 as a decimal. 1.5. It's exactly equal to 1.5. Here's the problem. What's 1/3? Yeah, it's 0.333 forever, right? Can you write 1/3 as a decimal and have an exact representation? You can't, because the decimal goes forever, right? It's irrational. We'll talk more about that, real soon. We'll talk about sets of real numbers, and we'll review that stuff also. So decimals in this case, because of that 1/3 and that 1/6, doesn't work so well. Okay. The trick that we're going to use, I'll tell you what the name is, and maybe that'll help. It's called clearing the fractions. Let me ask you this. How about that first? Let's just focus on the first term for a second. Can you think of a number I could multiply that by, an integer I could multiply that by, so that the denominator would go away? In other words, I'm asking the question. We're just kind of focusing on that guy. You fill in the blank. What times 3/5, and I guess we can include the x if we want to, is going to, what number could I put there that's going to give me an answer that doesn't have a denominator? It's not a fraction. 5/3, yeah, that would work. What if I want to multiply by just an integer, though? You're on the right track. I mean, I can still end up having a number on top, but I just want to get rid of the number on the bottom. So you're thinking about it right. What about just the 5? Yeah, 5 would work, right? If I plug in a 5, 5 is the same as 5 over 1. And then I could cross-cancel there, couldn't I? Right? Everybody agree? Okay, so 5 would work. What's another number that would work? If 5 works, what else might work? 15 would work. What's another one? 15 would work. 25 would work. 10 would work. 20 would work. What do those have in common? Oh, they're multiples of 5, aren't they? Everybody agree? Any multiple of 5 is going to cancel that 5 on the bottom. Does that make sense? Okay. What numbers? Now, what about the next one over here? So this one, I'd have to multiply. This first term, I'd have to multiply by some multiple of 5, right? Next term, it'd have to multiply by a multiple of 3. This one would have to get multiplied by a multiple of 2, and this one a multiple of 6. Okay. And how about this? would you agree that because 3 and 2 both divide into 6, that any multiple of 6 has to be a multiple of 3 and a multiple of 2? Does that make sense? Okay. So really, I've just got to find, if I want to take care of all this stuff at once, and remember, this is an equation, right? And that's important. Because this is an equation, what's our rule for equations? All the fancy rules of equality you can summarize by one simple statement, right? I think maybe we mentioned this yesterday. In an equation, I have to treat both sides equally, right? I've got to do the same thing to both sides. So whatever I multiply this side by to get rid of those denominators, I have to multiply the other side by the same thing. So I have to pick a number then, don't I, that's a multiple of all those. What is it? 30. It's 30. Yeah. Does that make sense? Here's how we could maybe show that. I don't think I think most people here, you guys probably just jumped right to 30. But here's how you could kind of think about the process just a little bit. If I took the multiples of 5, just make a list. 5, 10, 15, 20. Is this ringing a bell? 25, 30, 35, etc., right? What about the multiples of 6? 6, 12, 18, 24, 30, 36, etc. Well, where's the first time that we hit a common number? 30, yeah. Everybody see that? It's right here. Okay, so 30 is what we would say it's the least, it's a common multiple of all the denominators, and it's a special one because it's the least common multiple. What does it mean in math when we say least? Smallest. Yeah, it's the smallest common multiple. That's the same thing as a common denominator, isn't it? When we find a common denominator with fractions, we're doing that, aren't we? We're just finding the least common multiple of all the denominators. So our least common multiple, and a lot of times, have you seen it written that way, LCM? Okay. So the LCM is 30. And then all we've got to do is distribute that through both sides, and that's going to clear all the fractions. That special number that we picked. And we picked it because all the denominators divide into it, right? So this is what we can do. And if I want to write that as 30 over 1, I can't. There's one more trick with this. There's two parts to this, really good trick clearing the fractions. You find the least common multiple, or the least common denominator, whatever you want to call it, and when I distribute it through, let's think about an easy way to do this. Normally when I multiply fractions, I just multiply straight across, right? So if I multiply straight across, I'm going to get 90 over 5. Agreed? Real quick, what's that simplify to? 90 over 5. Come on, come on, come on, come on. It's hard to figure out, isn't it? A little bit. You got to think about that. You can get really big fractions if you just multiply straight across. Is there a way we could have done that more simply? What do you, I see it. You're thinking of it, Austin. You could reduce, couldn't you? Right. So how about this? Here's how I like to show this work. And I would encourage you to do this too. This is a good way to kind of keep track of what you're doing. 30 over 5 reduces to what? 6. Good. So that's 6, and then I put an arrow down and circle the top. So what we end up with is 6 times 3 then, right? Which is what? 6 times 3? 18. Good. So we get 18 and then an x, right? See how that works? Isn't that good? 30 over 3 is 10. Times the numerator. 10 times 1? 10. About over here. 30 over 2 times 3. 45. There you go. And then finally 30 over 6. 25. And then times x is just 5x. And I would say I'm not even going to bother going any further from there. Now, that's easy, right? From there we end up with a pretty simple problem to do. Actually, let's go a little further. There's one more point I want to make about this. Can I isolate x yet? Not quite. There's 2 x's. What do I have to do to get a single x? Subtract 5x. Good. So if I do that, I end up getting 13x, good, plus 10 equals. So what are the two steps in order to get x by itself? Subtract 10 and then divide by 13. So isn't that going to give me, let's see, 45 minus 10 is? And then if I divide by 13, I get 35 over 13. That's how I want to leave my answer. Okay, I know that going back, you probably in the past have been encouraged to write answers as mixed numbers. Like, what would this be? 2 and, what would that be? 2 and 9/13? We don't want to write that way anymore. We'll just leave it as an improper fraction. Now notice that my answer is a fraction, but that's okay, right? I didn't get the fraction until the very last step. I didn't have to do anything with it, right? Okay, does that make sense? Okay, everybody try number, if you haven't already done it, do number 7 on the homework. On these, on the one you just did, the least common denominator was 8, right? What if you used 16? Would it work? It would, because 16 is a common multiple of all the denominators. What's the disadvantage of using 16?
You have to reduce at the end.
You have to reduce the answer at the end. Yeah. It's easier to find the smallest common multiple. Okay, so next issue I want to look at. Something like this, okay? I don't even know, raise your hand if you've solved the absolute value equations before. Okay, you have. Good. Okay. So do you remember what the strategy is with solving an absolute value equation?
You get rid of it. Well, never mind.
You start
Say it again.
You start in between.
You would, if you were simplifying, you'd try to, and it's true, you would try to simplify anything inside the absolute value bars, right? There's nothing I can simplify there, though, right? Let me remind you, before we jump into this, let me remind you what absolute value does, right? What does an absolute value function do? If I have the absolute value of 4, what's that equal to?
4.
4, good. Okay, what's the absolute value of negative 4 equal to?
4.
4. So the job of an absolute value function is just to make sure that the output is positive, right? Okay? What if I have something like this? What if I had the absolute value of x is equal to 4? X could be 4, right? Because the absolute value of 4 equals 4. What else could x be?
Negative 4.
Could be negative 4, couldn't it? Right? So our goal when we're solving an absolute value equation is to get the absolute value part by itself, right? Because if I have the absolute value of hand, meaning we don't even care what's there yet, right? If the absolute value of hand is equal to the number a, right? And that's weird, but let's just let a represent any number, right? Then either hand is equal to, and we'll just call it, how about if we call it, we'll just call it x, that's fine. Either whatever is inside the absolute value bars is equal to a, right? I get two answers. Either x equals a or x equals negative a, right? Does that make sense? And that could have been more complicated than an x. It could have been an x plus 1, right? Or it could have been a 3x plus 1, right? It doesn't matter what's in there. Whatever is in there, inside the absolute values, either has to equal that number or its opposite. And then I just solve both of those equations individually, right? So let's look at an example with numbers in it. How about? So my goal here is to isolate this part, isn't it? I've got to get that by itself. Okay, that's okay. The stuff we've been doing still applies, doesn't it? That's the order of operations bottom to top, isn't it? Right? So what are my steps going to be if I want to isolate that thing? First thing I have to do is what? Subtract 2?
Subtract 3.
Add 2, right? my first step is addition or subtraction. What do I have to add or subtract to both sides to get this orange bubble by itself? Got to add 2, right? So if I add 2, those cancel, right? And I end up getting -3 times the absolute value of 3x plus 2 equals what, -6? Okay. Okay, multiply? Divide, right? Now I have to get the absolute value part by itself, I have to undo multiplying by -3. What's the inverse of multiplying? Dividing. Good. So we'll divide each side by -3. And on the left side, I'm going to get the absolute value of 3x plus 2, positive 2. Okay, good. So now, here's how you can think about this. Here's what I always tell my students. When you're dealing with an absolute value equation or an absolute value inequality, we're always going to make a trade. We're going to trade the absolute value thing, equation or inequality, for 2 normal things. In this case, 2 normal equations. Every time. You're going to make a trade, absolute value equation in this case, for 2 regular ones. What are the 2 regular equations? Either for the absolute value of this expression, hand, call it, for the absolute value of hand to equal 2, whatever's in there, call it hand, could equal 2. So either this stuff equals 2, or all this stuff in there equals -2. And that's easy, right? Now I've just got 2 simple equations to solve. In both cases, I'm going to get different answers, but the steps are the same. To isolate x, what are the 2 steps in order? Subtract 2, and then divide by 3. Okay. So over here, if I subtract 2, I'm going to get 3x equals 0. Divided by 3. Okay, now what about that? 0 divided by any number is 0. The rule is we can't have a 0 on the bottom. We can't divide by 0. But 0 divided by anything else is 0, right? So I just end up with either x equals 0. What about over here? Subtract 2 and I get -4 on this side. Divide by 3 and I get x equals -4/3. So those are my 2 solutions. How could I check? Plug them in. Okay. Go back to the original equation. If I plug in 0, what would I get? So I would end up getting 3 times 0 is what? 0 plus 2. What's the absolute value of 2? 2. -3 times 2 is? Plus -2? -8. How about that? And then the other answer was, what was it again? -4/3? So 3 times -4/3, what's that? Yeah, you are. Yeah. What's 3 times, if I plug in, let's look at that one. If I plug in -4/3, I'm going to get -3 times the absolute value of -4/3 times 3, right? Plus 2 minus 2, is that equal to -8? Well, if I multiply these fractions, I could cross-cancel, right? So -4/3 times 3 is just -4, right? So that gives me -3 times the absolute value of -4 plus 2. Here, let me kind of partition this off, so we'll work in here. Minus 2 equals -8. -4 plus 2 is -2. What's the absolute value of -2? Positive 2. What's 3 times -2? So all that stuff becomes -6. Is -6 minus 2 equal to -8?
Yeah.
It is. Check. So it worked. Right? Does that make sense? Yeah, they both work, yeah. And you have to check them both. Yeah. Okay, try one of those.
Wait, you have to check them both for it to work?
Yeah, they both would have to be true for it to work. So why don't you try, I don't care which one, just try one of the bottom ones. How about number 11? Do number 11. Okay, so on this problem that we're all working on, let me write it down. So we have 3 times the absolute value of x minus 5 equals 27. Now, a real common thing that people want to do, and I totally get why this is, because if those were parentheses instead of absolute value bars, we could distribute to 3, couldn't we? Okay, you can't do that, though. You can't do normal math with absolute value functions. Okay? We can't do this. We can't distribute that 3. If we distribute to 3, we're going to get a wrong answer. Okay? What do we have to do instead? We got to isolate the absolute value, right? The pink part. We have to get this stuff by itself on one side of the equation, and then I make my trade for 2 equations. So don't distribute. Okay? Instead, we want to isolate the absolute value of x minus 5. So what does that involve? Divided by 3. Good. Divide both sides by 3, so those cancel, right? And then we end up with the absolute value of x minus 5 equals 9. Okay, good. And that's important because, look, now we've isolated the absolute value, right? Once we isolate the absolute value, we make our trade. We're going to trade for 2 regular functions. So the next step, we're going to trade absolute value equation for 2 regular equations, right? So what are those? Either
x minus 5 equals 9.
Good. Either whatever's inside the absolute value equals 9, or
x minus 5 equals negative.
and then I just solve. Okay. Make sense? All right, so last issue for today. Last issue for today is, let's just, and this is just kind of a generic, it could be, we're going to look at word problems, you know, kind of applied problems all year. Let's just take a quick example and let's talk about how we approach these things. What do you do with a story problem like this? Let's read through this. Bobby is 4 years younger than twice Jimmy's age. If Bobby is 26 years old, how old is Jimmy? Okay? So what do we do with a situation like that? This is where algebra really is helpful, because you can make short work of problems like this. Okay, one thing, we got to assign a variable. First step was we always wanted to find some variable that we can use to rewrite this mathematically. So what could be our variable here? Okay, yeah, and a lot of times when we're trying to assign a variable, it comes from the question itself, doesn't it? Right? So what's the question that's being asked here? How old is Jimmy? Okay, well then let's let x or j or whatever you want to call it, let's let x equal Jimmy's age. So that's going to be x, right? So if we're trying to find, oh sorry, yeah, okay, that's fine. Okay, so if Bobby is 26 years old, how can we make an expression then to represent this stuff. Bobby is 4 years younger than twice Jimmy's age, and Bobby is 26.
52 minus 4 equals X.
Okay, but how'd you get, you're on the right track. How do we say this first part? Bobby is 4 years younger than twice Jimmy's age. What's twice Jimmy's age?
22.
Well, that'd be 2x, right?
Yeah.
If Jimmy's age is x, then twice Jimmy's age, I'll try to color code this. Twice Jimmy's age would be 2x. How about, let me color here, how about
Equals Bobby, which is.
4 years younger?
You got to subtract 4.
Subtract 4, right? And that's equal to,
Bobby's age.
which is 26, right? That make sense?
Yeah.
Everybody see that? And now, what happens if we solve for x?
Subtract 4 to get.
That's Jimmy's age, right? So if we add 4, 2x equals 30,
Divided by 2.
divide by 2, x equals 15. So that's Jimmy's age, is 15. Make sense?
Yeah.
Okay? That was a quick one, but we're out of time. You'll get plenty of practice. Just wanted the important point I want to make there is you got to pick a variable that you can write everything in terms of, right? And usually that variable comes from the question that's being asked. Okay?